Gravity is one of 4 known fundamental forces in our universe, and gravitational forces are a major topic of a first course in physics. However, another fundamental force is the electromagnetic force. It turns out there are many similarities between these two, but you'll also see there are also some major differences. 2 pieces of plastic tape, for example, can be observed to be significantly attracted to Earth because of Earth's large mass. However, the tapes cannot be easily observed to be gravitationally attracted to each other. When the tapes are charged electrically, however, significant electrostatic forces can act upon them. Simply take 2 pieces of plastic tape, stick them together front to back, and then rip them apart vigorously. You'll see how strong the electrostatic force between them becomes. In a lab involving sticky tape, you can see evidence of 2 types of charge. One tape will acquire what's called a positive charge, and the other tape will acquire a negative charge. Benjamin Franklin is known for giving these charges their names. If you make several sets of tapes, you'll find that top tapes are attracted to bottom tapes, but top tapes are also repelled by other top tapes. This is a difference between gravitational forces and electrostatic forces. Gravitational forces are always attractive, whereas electrostatic forces can be attractive or repulsive. We'll also see that electric forces are much stronger than gravitational forces. This can be seen in the sticky tape experiment. You'll see that the strength with which the tapes attract each other is stronger than they're attracted to Earth even. Let's look at 4 combinations of particles here. Which pairs of particles will experience an electric force between them? Here we want to treat the particles as points of no volume. Now, in a sticky tape experiment, you'll find that charged tapes will attract neutral material, such as paper and tinfoil. The reason for this is that at the atomic level, what happens is, if you take a neutral object, it's got protons and electrons in it. And if there's no electric field nearby, then they'll just be randomly organized. However, this object can become polarized in the presence of a sticky tape that's been charged. So let's say we've got a charged tape here. That would be a top tape. It's positively charged. And let's say that it comes near a neutral material. What will happen is the negatives will want to hang out such that they are closer to the thing they're attracted to. They're attracted to the positives of the sticky tape. And so on average, we see that the dipoles of positive and negative will align themselves so that the negatives are close to the positive. And what this can do is create a weak attraction between the 2 objects. This is what happens in an insulator. In an insulator, the negatives are not allowed to escape their positive counterparts very easily. All they can do is wander a little bit. However, if we have a metal, such as tinfoil, and let's say that it becomes polarized, because of the presence of a positive sticky tape, what will happen now? Well, we'll have a very rigid lattice of positive particles. That's common in a metal. And a lot of the electrons, though, are free to move around throughout the object. So those negatives will venture off to the right here so they can hang out near what they're attracted to. This creates a much larger force between the objects, and that'll be observed if you do the experiment. I bring this up because I want to show the differences between a macroscopic large object and a point mass. These are simply represented as points. They have no volume and no room for particles to rearrange. These neutral objects cannot exert an electrostatic force on each other. Interestingly, objects of significant volume can. How could this happen? Well, if you have two neutral objects near each other, they're all made up of protons and electrons. However, we know that protons and electrons are attracted to each other. So, in the same way that this positive is attracted to the negative that's near him, and in the same way that this positive and negative is attracted to each other, we would also find that the negative of one will be attracted to the positive of another. Now, because they're separated by a large distance, the attraction is not that great. But the particles will line up. The negatives of one will want to be as near as possible to the positives of the other. And so they'll polarize. It's going to create a very weak attraction between the two. It's certainly something that's so small that it would be barely perceptible. In chemistry, this phenomenon is called the London dispersion force. Our point masses here will not exert that London dispersion force between them because they have no volume for their subatomic particles to rearrange geometrically. So we will see no electrostatic force here. So what is the C? C stands for coulombs, and it is the unit of electric charge. It's how we measure it. So if we have a positive 1 coulomb on the left and a negative 1 coulomb on the right, they will certainly be attracted to each other strongly. What if we have a negative 1 coulomb near another negative 1 coulomb? This force will be repulsive, with the same magnitude as the force above. Now, what if we have a positive particle near a neutral particle? Well, if we treat that neutral particle as a point mass, there will actually be no electrostatic force.